And now you are at the point where one of the last things that we don't understand as humanity is quantum. It doesn't intuitively make sense to anyone. We'd never shown logical qubits as humanity before 2023, and now we have them. The most precise way to keep time and the most stable way to keep time is the energy transition of an atom. The underlying photonics and the underlying components are really the same to build a quantum clock and to build a quantum computer. That's actually really taking advantage of the superposition of the atom. Sometimes I joke that the only thing better than quantum is quantum in space, but
Yes!
yes, but it's actually, there is a huge market for quantum in space. Neutral atoms has indeed emerged as the leader on most of the metrics that matter for quantum computing.
Disruptors and curious minds, welcome to another episode of Thinking on Paper. My name's Jeremy. This is Mark. We unpack the future with the people building it in real time. Today, we're back in quantum. I'm super excited, but it's a new angle to quantum. Mark, take it away. Where are we headed? What are we doing?
We're going into a modality of quantum that we haven't learnt about before. We've done trapped ion, we've done superconducting, we did spin qubits a few weeks ago, and this is new ground for us. So very excited to learn more from our guest, Matthew Kinsella, the CEO of Infleqtion. And we're talking about neutral atom quantum computing and all the wonderful solutions to some of the world's biggest challenges that it might be solving. Welcome to the show, Matthew. Thank you for thinking on paper with us.
Great to be here, Mark. Great to be here, Jeremy. And thanks for having me.
It's our pleasure. It's our pleasure. I want to start high level and think about what all of this means, but I want to root that in something relatable. So I want to talk about coordination. How important is just the idea of coordination to your work and what you're doing?
I love that question because I can go many different ways with it. So let me take a couple cracks and I'll talk about coordination internally at Infleqtion, and then I'll talk about what quantum can do to help coordination for humanity. Infleqtion has a different strategy than most quantum companies, and it's largely due to the flexibility of the neutral atom modality, which you both mentioned. You mentioned that modality in your introduction. And so unlike spin qubits or superconducting, or in some ways trapped ions, neutral atoms is useful for tasks beyond just quantum computing. And the neat thing about that is the underlying components and the underlying technology is the same. And so when we build some of our quantum sensing products, and we can get into more depth into what those are or why they matter, that directly impacts how we're doing on our quantum computer as well. So there's a deep coordination in the underlying R&D that we need to do here because it cuts across our different various product families. So coordination internally, even in just that one example, is incredibly important. If we zoom out to the how quantum might help us coordinate to better get our kids to lacrosse practice or in other types of ways, and you think about time and what role time plays in coordination. Part of it is obvious, but much of it is not. And let's talk about GPS for a minute. So what is GPS? GPS is a position, navigation, and timing system, a PNT system. In reality, it's a lowercase p, lowercase n, capital T. The time that comes down from GPS is actually the most important service that it provides. So there are precise clocks in the satellites that make up GPS. There's about 30 of them. And those clocks are reasonably precise themselves, but they synchronize with these very precise room-sized clocks down on Earth's surface. And so they have to discipline to those clocks. And then they send that timestamp down to our iPhones or to servers or to basically everything on the planet. And in order to coordinate, we must synchronize. And so we rely heavily on GPS for all of the synchronization and coordination that we do here. So think about the electricity grid, think about the RF networks, think about GPS, think about financial markets. Everything has a timestamp that all comes from GPS. And GPS is getting increasingly spoofed and denied. And so we can't rely on it as much as we used to be able to. It's getting fragile. And quantum, and in particular quantum clocks, can actually provide better than GPS precision timing locally in an unspoofable, unjammable way, allowing us to A, coordinate with greater precision because they are more precise than the timing coming down for GFS, but B, guard us against the denial and spoofing of GPS, which could really disrupt coordination globally, which would be a total disaster.
What is a quantum clock and how does that link to GPS?
Great question. I mean, time, we could go down a deep time rabbit hole, and it sounds like you all have done that. I will answer your question, but just because it sounds like you've nerded out on time a little bit, it really has been a fascinating experience for me just to get to understand the role that time plays in our world and how that's changed over time. Before the railroads connected cities between each other, time was a very relative thing, right? It didn't matter if your concept of time matched up to the concept of time in the town next door to you. But once they started connecting the towns, they had to synchronize their clocks, right? And because you had to have a general idea of if you're going to arrive somewhere, was it on the same, the same time zone as where you were leaving from? And so there was those timetables, and there was actually a day, and I believe it was in the 20s or maybe the teens, where for the first time ever from New York, they broadcast a time that was nationwide, and they synchronized time for the first time ever across, from the East Coast to the West Coast. And before then, it was just a very relative thing. And then since then, we've been getting more and more precise concepts of time. So to answer your question, what is a quantum clock? Well, turns out the most precise way to keep time and the most stable way to keep time is the energy transition of an atom. And so you can think about, the earliest clocks were pendulums swinging back and forth, right? And then it turned into springs inside of stopwatches and the like, and then moved on to quartz, which you put an electric signal into a quartz and it vibrates at a reasonably stable frequency. The actual best and most precise and fastest way to tick time is with the energy transition of an atom. And so what we do is we take advantage of that atom's effectively quantum nature by shooting those atoms with lasers. We use rubidium atoms because it actually has really only one outer valence electron, so it's easy to manipulate. We hit that with an ultra high frequency laser, in this case 778 nanometers, and that causes the atom to effectively go into excited ground, excited ground, excited ground. And that energy transition happens at a very stable rate, and it happens very precisely and very, very quickly. And so by hitting these atoms with the right resonant frequency to what it excites them, that becomes a very stable frequency reference. And that's how we build a quantum clock. And it's only been possible more recently because of the advances in laser systems to be able to have that precision to hit those atoms with these lasers at that level of precision.
So Matt, I like to insert a musical reference in nearly every show. So would you say this 778 nanometer laser is essentially the atom's metronome?
Nature's metronome.
Yes, I think that's a reasonable way to think about it, but I might flip it. I would say that the atom is effectively the metronome, and you have to find the general frequency that excites the atom, and then you have to tune that frequency to get just right. The atom is gonna do its energy transition at the way it does it. That's sort of predefined by nature. It's the laser that's like, almost think of it as maybe like the battery for the metronome to get it going, and then the atom itself is the metronome, and it is nature's metronome. I love that analogy, and you're never going to get more precise than nature's metronome.
Is this what allows you to perform your operations at room temperature? Could other quantum computing modalities give the same time?
An ion could. I don't believe superconducting material could, and spin qubits I don't know. There are clocks built on ions. Ions are really just an atom with a charge. And in fact, it's funny, there's a bit of our founder, Dana, will sometimes refuse to use the term neutral atom. He just wants to say atom because the term neutral atom really only exists to differentiate it from ions, which carry a charge. And so Dana sort of was like, well, why do we need to be the ones to add neutral? Why can't we just be atoms?
So neutral is a marketing term for it. That's more than anything. Yeah.
It's true. Yes. Yeah. Funny. Yeah. We're just working with atoms that don't have a charge. So good question as to whether you could theoretically use those other technologies. You could use ions, but I don't believe you could use some of the others. And so, but your question is a very important one and leads really into our broader strategy. And so it's the flexibility of the neutral atom modality that, in my mind, was so intriguing to me when I was first exposed to it back in 2018. Like I said before, the underlying photonics and the underlying components are really the same to build a quantum clock and to build a quantum computer. So let me flesh that out in a little bit more detail. So simulating these atoms with lasers, and we're flipping the atom from excited to ground, that's actually really taking advantage of the superposition of the atom. And so if you've had quantum guests on your show before, I'm sure you've used that term and know that that's one of the fundamental building blocks of a quantum computer. So the clock really helps us master superposition. We can also then turn those atoms into what's called the Rydberg state. So if you remember, we were going excited to ground to take the ticking of a clock. The Rydberg state is what is, you could think of it as like the electron way out in outer orbit. And so it's a very, very big atom. And when it's in that state, it becomes sensitive to the entire frequency spectrum. So this is actually completely game-changing technology. If you've studied classical radio frequency technology, normally you need a metallic antenna device that vibrates at a given frequency. And normally that device needs to match the size of the wavelength it's receiving. So for the very low frequency, long wavelength signals, you need these massive, massive antennas to receive them. What we can do is we can turn those Rydberg atoms, those atoms in their Rydberg state, into antennas themselves, and they can receive the entire frequency spectrum. So you can receive a very low frequency, long wavelength signal on something the size of a sugar cube, because the atoms are actually picking up the electromagnetic frequency and then doing all the signal processing that you'd normally need to do. It's sort of magical almost. But what's important about that is that Rydberg state is the state that you need those atoms to be in to entangle them. So now we've got the second building block of compute. You asked is what allows us to do this at room temperature? And the answer to that is, what is room temperature and what is cold, right? And so most of us think of cold as a freezer, but really what is cold? It's the lack of motion of atoms. And since we've already really become experts at controlling atoms with lasers, the next logical step is just to hold those atoms in place such that they move so little, they become the coldest place in the known universe. And so part of what I was saying with, before with atoms in a vacuum, that's like outer space in your hand. These atoms are colder than outer space. They are moving less than they would move in outer space, but the system itself is at room temperature. So we are putting them into ultra cold states, but by doing it we're doing it with lasers. And so that's what allows us to do this all at room temperature. And that is actually what gives the flexibility of this modality, because if you need to reside inside a freezer, you're not going to be able to shrink that freezer. You're not going to be able to cost that freezer down. Those are mechanical systems. Everything we build is based on photonics, these vacuum cells, and then electronics, which can now be shrunk into our clock is 3 pizza boxes or so. Its end state will be chip scale. Because we can integrate all these photonics. And so it's the field deployability, it's the ruggedization, it's the shrinkability, it's the cost down that makes this technology so special. And because we can then engineer those systems, and they're all sort of the building blocks of quantum computing, Neutral Atoms has indeed emerged as the leader on most of the metrics that matter for quantum computing as well.
Awesome.
So is it Rydberg state?
Rydberg,
Rydberg. All right.
Yeah.
So the Rydberg state, instead of a 1 and a 0 qubits, has this potential of being in any one of those states between the 1 and the 0, like infinite states. So
infinite states, yes.
So this Rydberg state opens up that spectrum of potential for the atom. Is that where we're headed?
The Rydberg state is a state that's close to an ion. So you can think about, like, if it got a little more excited, it'd become an ion. And one of the reasons why trapped ions got the head start in computing going back 20 years is because it's easier to control ions because of that charge. You can actually, they repel each other. And so you can sort of use that repulsion to get them into their little qubit spots, right? And by just using microwaves, and then you can start to simulate them there. Rydberg state still does not have a charge, but it makes these atoms easier to control. And so that's why we use the Rydberg state. The superposition and the ability to be in multiple states at once is present in really all qubit modalities. But in order to really harness that, it must be in the ultra cold state. So the Rydberg state happens to be, make these atoms sensitive to their RF spectrum, but it's the ability to control the atoms and then individually address them and then freeze them in their Rydberg state, which is what allows us to actually harness the superposition of those atoms, if that makes sense.
You've just announced that you have an atomic clock in a UK submarine.
Yes.
And I'm from the UK, so I'm very happy about this. We are the oldest, greatest naval country in the world, don't forget.
Indeed.
How did you end up with a quantum clock in a UK submarine and not an American submarine?
We have a substantial office in the UK, in Oxford, actually. We have about 55 folks there. And so, and one of the reasons for that was the UK has been, frankly, faster moving on quantum than the US. They identified it back in 2013 as an absolutely critical national priority. And so we felt it was important to have feet on the ground there. And so we started our office there in 2018, and it's grown to 55 people. So the Ministry of Defense and the UK government in general is one of our largest customers, and we have a great relationship with them. So they had just announced their first underwater autonomous vehicle, and it was called Excalibur. And they were going to take a maiden voyage. Yes, they were going to sail it on its maiden voyage, and they got the opportunity to put a payload on it. And so they decided what payload would we want to put on this, and a quantum clock was what they wanted to do. So it was not only was it us putting a quantum clock on a underwater autonomous vehicle, it was really the first thing that had been put on this vehicle. And the reason why they wanted to put a clock on there is actually because underwater you don't have access to GPS. And so you don't synchronize the GPS unless you surface. And surfacing is very important to kind of get all of the inertial sensing equipment and range finding and direction equipment that's on a submarine, because those aren't quantum in nature. So therefore they have errors, and therefore they drift, and that drift compounds. And so if you were to try to sail a submarine from the UK to the US without going up and synchronizing to GPS to get all your systems back in order, you'd be off by hundreds of miles, because it starts off small, right? But then those errors compound, and next thing you know, you're going, who knows where you're going. So one of the reasons that they wanted to put a clock on there is it's the beginning of being able to build an inertial sensing system, a position navigation timing system that's completely independent of GPS. And timing is a very important part of that. So having better than GPS timing locally on the submarine that doesn't need to synchronize the GPS is critical.
What did you learn from that little experiment?
We learned a lot of stuff. We learned, and it largely had to do with the engineering of our system. We learned that it could function 30, 50 meters underwater. We learned it, which we can learn it could, function in the very coldness of underwater. And so it wasn't so much we learned too much about the ability to keep time. We learned more about how did we engineer the system, and can it work out in the field? And that was invaluable information. It turns out it worked very well, which is great. And we have funding to put these clocks in space also. So to space harden these clocks. And ultimately, I think that it sounds, sometimes I joke that the only thing better than quantum is quantum in space. But yes, but it's actually, there is a huge market for quantum in space.
Is that what you're doing with Voyager?
Ultimately, yes. The idea is that we will work with them to get clocks up into space, and then start to test them in some of the real estate that they have on the International Space Station. And so the interesting thing about getting things ready to go to space, and we were the first company to ever put quantum technology in space. We did it back in 2018. It was part of what they called the Cold Atom Lab, and it still resides up there on the International Space Station. Much of what needs to be done is the mechanical engineering to radiation harden or to survive the crazy shakes that happen during blast off. And so it's not really fundamentally a different product. It's just engineered to work in the absolutely crazy situation that space is.
Link to listeners, we just recently had a conversation with a company who are doing radiation proof transistors and technology. So I'll put that link in there, because it's another thinking on paper node, Jeremy, connecting these.
I love it.
Yeah, Matt, one thing we wanted to share too is a lot of what we're trying to do after 2 years into this. We're creating a knowledge graph of the interdependencies between all of the things that we talk about, the tech side, but also the human element side. So government, equality, access. That's what Mark is referencing, that hopefully we can continue to do it.
No technology is a silo anymore. No technology is an island. They're all interconnected, and they're all very much reliant, dependent on each other.
So true. So true. Yeah.
Mark, how do you feel about going down the path of the hybrid classical? I've got a couple of questions in that world.
I think that's good, because that relates to AI as well, I think, and
it does.
And what's happening in Illinois.
Yes, absolutely.
If we could frame that in a quantum computing workflow, and you have a classical node and you have a quantum node, and you have a workflow you're trying to organize between the two of them. Talk about what you've built and what interesting things could shake out from that.
One of the most important things to understand about quantum computing is it's not going to replace the things or the workloads that we're doing in classical computing. It's going to open up whole new workloads. And so I don't see this as necessarily a disruptor to GPUs or classical computing at large. it will be an expansion of what humanity can throw compute at. Let's call it that. So the vision of the future data center that I have is just like GPUs layered in on top of CPUs to enable new use cases. You're going to have quantum processor units, or QPUs, sit above those, and workloads will get sent into the data center in the cloud, and they'll be chopped up, and the various parts of the stack are best suited to solve. The workloads will be sent to those parts, and so the underlying infrastructure to do that is something that we focused a lot on, and we focused a lot on it with Nvidia. Nvidia is really taking a leadership position in that bridge between quantum and classical. And so they announced something called NVQ Link in October of this year, which is really exactly that. It is the bridge to allow workloads to pass really seamlessly between quantum computers and classical GPU clusters. And a good example of how that might look in the future is something we did with them just about a year ago, where we solved a very basic material science problem called the Anderson impurity model. It's a photovoltaic model. Parts of it were solved on a GPU cluster, but parts of it that wouldn't have been able to be solved by GPUs were solved on our quantum computer. And then they recombined to give the answer. And we talked a lot about how nature does quantum better than anyone. Quantum is really the computational method of nature. And so the types of problems that quantum computers are going to be very good at solving are those that are really rooted in nature themselves. And so the ability to model the interactions of electrons when you're combining different molecules, that's inherently quantum mechanical in nature. And even the most powerful GPU cluster at the end of the day is boiling everything down to zeros and ones, right? And that's not how nature fundamentally works. And so these types of nature-based problems break on classical computers because they can't be boiled down to that heuristic of 0 or 1. And so a lot of the parts of that Anderson impurity model could be, solved by the classical computer. So it was the combination of the two that was what made us able to do something that had never been done before. I think you can think about that as a very not commercially useful example yet, but you expand that over time, and that's how we're going to build better batteries, right? Instead of your iPhone having to be charged every night, you could build a battery that lasts for a year maybe, right? Or much longer, and or help solve the Haber-Bosch process, which is what we use to build fertilizer. And we've been trying for 100 years to find a better catalyst, but it's just too complex to model that interaction. That's the type of thing that quantum computers will be able to do in tandem with classical computers.
Is it fair to think about classical computing as a bit of a brute force modality, and then quantum as more of a finesse driven modality?
Yeah, I think that's not a bad way to think about it. You are boiling all of life's problems down to Boolean 0 or 1 logic, and what we can do by boiling life's problems down to that type of logic is incredible, right? It's amazing what you can do with doing that 0 or 1 billions of times, but that's not fundamentally how nature works. And so, yes, we're kind of brute forcing these problems. And that's why I think you see the power consumption issues when we're starting to throw classical computing at problems that it maybe wasn't well suited to solve.
Can I ask a silly question?
Yeah.
Part of the computation that was done on these were your quantum computers?
Yes.
So could you explain, because in our heads, obviously we all have the big chandeliers. We've spoken to IBM, they have the huge quantum computers. And from what you're saying, yours are much smaller. Could you speak a bit about the algorithms or the software that you're running on those as well? And are there bridges in place that link the softwares between quantum and classical computers? And that's my silly question, because it might not even make sense.
No, it does. It does. And I do think software isn't talked enough about in quantum computing. Even at the most basic level, we're shooting atoms at lasers, but it's not like I'm sitting there with a laser gun shooting the atoms. We are programming these lasers with software to do this at very, very precise, literally atomic level precision. And so how does the quantum computer work? Well, at the most basic infrastructure level, it's atoms interacting with lasers. And then there's a software layer that's sort of programming each of those laser shots, right? And so that you can think of like the equivalent of binary code, right? Or binary language. And then there's a stack that abstracts that away, because we don't want developers to have to think about how you're interacting with each individual laser, and atom. And so now you have middleware layer, which we call superstack, which interestingly we use on our own systems, but it does work across modalities. So we have spin qubit customers, we have superconducting customers who use our middleware layer as well. And then the application layer is really, that's what we still need to do a better job, I think, defining. And that's where we need to get the developer community really activated. And it'll be easier as the computers start to do things that are commercially useful, because they still really are in the realm of doing cool physics experiments and doing things that you can extrapolate commercial value out of over time. But we're not quite there yet. And we can talk about when I think we'll get there and how we'll get there. But software is absolutely critical. And then the NVQ link that we were talking about from Nvidia actually fundamentally is software based in many ways. And so it's the software translation layer between classical and quantum computing.
Okay, thank you.
So back to this reimagining of the data center stack. We've got, CPU, GPU, QPU. Let's talk through where this bridge lives in a practical example. So I'm a researcher. I've got a question I want to have quantum computing help me with. Let's make one up. It doesn't have to be right. It's just something to illustrate the process. And when that question goes in, how does it break up? How does that bridge go? Hey, this piece goes to the GPU, this piece goes to the CPU, and this piece over here, we're going to let quantum mess with it.
So drug discovery is a way to fit that in, maybe as an example.
Sure. Yeah, we could try drug discovery example. And just to caveat everything I'm saying now, we're getting into the realm that I might be getting below my my depth. I'm not a quantum physicist. So
we aren't either, so it's all good. Yeah.
Our PTO Pranav will probably be able to answer this far more eloquently than I can, but I'll take a stab at it. Let's use a drug discovery example. So similar to how I was talking about, it's very difficult to model the electron interactions for a material discovery type process, because those are quantum mechanical in nature. The same holds for combination of molecules to combine them to build drugs, right? And the type of problems that quantum computers are going to be good at solving, I usually think of as small data problems. So there's not a huge amount of variables necessarily, but when you start combining those variables, the outcome approaches infinity. And that's the type of problems that just break classical computers. And those are really the way quantum mechanics work, because of the absolutely massive range of potentials of these electrons combining and the molecules combining. And so we use a drug discovery example. Let's say we were trying to, I don't know, name the drug, some drug to cure a particular type of cancer. And I'm not an expert on how drug discovery works now, and I know we're utilizing AI to be much more efficient at it, but it's still kind of brute force, right? You're taking educated guesses. You're using AI to narrow down the possibility of which molecules might work to help with this ailment, but it's still brute forcing the problem. With quantum, you can really do it in a more, I guess you use your word, elegant way, and actually model out how these will interact. And you could probably cut the development time down from months to much shorter periods of time, because you can run these simulations simultaneously. So how would the underlying software layer know which parts to send to the GPUs, which parts to send to the QPUs? I actually don't know the answer to that question. It's probably going to be quite human directed until the software gets better. But I think most of the physicists would know, okay, this is the part of the problem that is really challenging for our computer now. We're going to try to start to dip our toe in the water of quantum and send those workloads to the quantum part of the computer and then recombine them for the answer. And so I think that's really the way you'll see this play out in reality, is people like drug discoverers or people like DuPont, who's building chemicals and materials, right? They'll start to experiment with sending small parts of what they're doing to quantum computers, and then that part of what they're sending there will just grow and grow and grow until they'll figure out how to utilize it in the most efficient way possible.
I'm on this thread. I'm not letting go of this thread of bridges. Similar to like traditional simple computing, you have an MCU microcontroller unit, and then you have a DSP, digital signal processor, right? And I think there's similarities based on what I learned about that, where the MCU kind of looks and goes, man, this is really hard work. We need to outsource this and chuck it to the DSP. So I think there's a lot of similar roots in old technology that you're talking about now. That was more of my own connecting of the dots, but I think it's applicable.
And just to stick on your bridge theme here, because I think this is pretty neat. When you write software, and going by software for quantum computers, you have to write it in a fundamentally different way, because you actually have to code around some of the laws of quantum mechanics. And one of those laws is called the no cloning theorem, which is very interesting. You can't copy and paste quantum data, which copying and pasting data is like it's all over the place in classical software, right? And so when we write our software for our quantum computers, we write this kind of very different software that doesn't do some of the things that would be very natural to do in classical software development. And that means we have to sort of re-architect the memory. But what we did was we started to run this re-architected memory software on GPUs. And it turns out that that actually provides some very interesting performance enhancements to GPUs, largely around the enlargement of the context window, which is one of the fundamental scaling bottlenecks to GPUs. And that's because the memory is totally re-architected. It's quantum in nature. And so we've kind of been trying to bridge the gap between classical computing and quantum computing hardware by software, and giving some of that quantum advantage to classical computing kind of via software, and rewinding or bringing forward the time to quantum advantage by software. So that's a kind of really interesting bridge we've been working on.
That's really cool because, like you said, the context window issue is real. Like that's a real bottleneck to scaling. You'll have to keep us posted there. That's really interesting.
We just announced a really cool contract with the Army. It's called Sapient Secure AI for PMT. What they're and this is based on our what we call contextual machine learning software. So it is our contextual machine learning software running on edge GPUs like Nvidia's Jetson, so small GPUs that don't have a ton of power or memory on them, and allowing them to ingest far more streaming data. So think of like video data, speed data, inertial motion data, and process all of that multimodal sensor data right there on the edge, which would have normally overwhelmed the memory capabilities of that GPU. But this allows them to expand it and then recreate some of the basic things that GPS is giving you, like where you are in the world, by extrapolating by all the different external signals that can be brought in onto this GPU. And so that's where the name Secure AI for PNT comes from. And so that's a kind of very interesting near-term use case that we're working with the Army on. But yeah, it wouldn't be possible without this software.
It's fascinating, fascinating. How can I weave a bridge into this question? What do you believe about quantum computing and quantum mechanics, but quantum computing, that your peers and your colleagues and the mainstream media or the mainstream narrative on quantum wouldn't agree with you necessarily?
There's a lot of different answers why I'm hesitating, but the one that keeps jumping to the top of my mind is the cohesion and the linkage between the quantum sensing products of the world and a quantum computer. Because a lot of times someone might look at classical technologies and say, what the heck does a clock have to do with a computer? Why would you build both of those things? In the world of quantum, though, they are actually sort of the same thing, just in different levels of complexity. So we've already talked about that. And if I think about the messaging that I'm constantly trying to explain to people, a lot of times people will say, well, why are you even doing these other things? Quantum computing is such a big market. Why don't you just focus on that and drop these other distractions? And I disagree with that fundamentally for many, many reasons. One, because these other markets are actually very large opportunities, and we've already talked about the DNA that we need to build in the company. But they're kind of the same thing, right? And so as we build the clock, we harness the superposition of the atoms. We just get better at building the computer. And so I think that is something that is not intuitive, but I deeply believe. And as I explain it to people, I think they come around to understanding it. But it's not the mindset people come in necessarily right away with.
I like that. I like that. Hey, let's ground it in something that people understand that we could apply today, and let's learn, because it's the same thing that you're applying, just in a different way. It's the same use of a technology that you apply to new use cases. That's why you're a technology company and not a compute company.
Yeah.
Right?
I know everybody wants to compare themselves to Nvidia because it's obviously self-serving to compare yourself to the largest company in the world. But that said, like, we really did take a lot of inspiration from Jensen's strategy, which he had this graphical processing unit that he pointed at graphics first, right? He pointed at video games, and he pointed at crypto mining and physics. And then ultimately the crown jewel of generative AI came around. But he didn't just wait for generative AI to come around to start to build and deploy. He addressed these markets along the way. And that's kind of how I think about what we're doing with neutral atom quantum tech.
Having orbited his space and Nvidia's space for a while, I don't want to make it about him, but what do you think drives his curiosity?
I don't want to speak for Jensen, but I think the world Jensen kind of boils down to how do I sell more GPUs? And so I think he's curious about how quantum helps him sell more GPUs is my guess. And I think, that idea of expanding the types of problems that we can address with compute, I think fundamentally it'll just mean more GPUs will be needed to work alongside QPUs. And I think that's ultimately why Nvidia has a really world-class quantum team internally. And a lot of it though is in service of figuring out how GPUs play a role in quantum going forward. And there are many, many ways. We talked about, the ways that they'll work together to solve problems, but actually I think, I know AI, GPUs, LLMs will help us get to quantum advantage on the computer faster, because a lot of the things we're dealing with right now are just errors in the qubits, right? We need higher quality qubits, and error correction is something we focus on as an industry, and certainly here at Infleqtion. AI helps you with error correction because these are kind of inference problems. You are having to infer where the errors are coming from and then correct them, and AI can help with that immensely.
I've got a question that we ask a lot of our quantum guests. There's just this debate over more qubits or better quality qubits. How do you feel about that, one way or the other?
Having a certain level of quality is of the utmost of importance. Beyond that, you can start to solve quality with quantity. And so to me, the ability to scale physical qubits is the most important, as long as they're above that threshold level of quality. Now, higher quality is better objectively. So continuing to get to, we're at 99.73% gate fidelities. That's the measure of quality that you use. And that's basically how well do the gates do what you want them to do, basically, right? The entangled qubits. We do need to drive that to 3 nines, 4 nines, 5 nines over time. But when you're at that level, really above 99.5% or so, you can start to solve some of the quality issues by throwing more quantity at them. And the term that I think is the most important thing to focus on to understand where we are, our progression towards quantum computers being commercially useful, is a term called logical qubits. And logical qubits are very high quality, error corrected clusters of physical qubits that can actually be used for computation. Physical qubits themselves are too error prone. They don't really do anything useful. And so, and this is why I have such high conviction that quantum computing is going to become commercially useful in the defined time period. One of the knocks it always gets is it's always been 5 years away. And I totally accept that is the case. And it always has been. This is the reason why I think it's actually 5 years away this time, is because of logical qubits. We'd never shown logical qubits as humanity before 2023. And now we have them. Only a handful of companies have them now. Infleqtion's one of them, but all we need is more logical qubits. And so we have the fundamental kernel of the ability to do calculations on quantum computers now. We really didn't have that before. And as we scale logical qubits to 100 logical qubits is about the level most people think we'll start to see some quantum advantage in the material science world. It's not going to be like the ChatGPT moment, I don't think, but it will be the first time we've been able to do something that is commercially useful in quantum computing. And so now it's just a matter of engineering, really. It's not any kind of physics breakthrough that needs to happen.
We started the conversation on coordination. Let's end the conversation on coordination. We are now going to align our atomic clocks to land the Thinking on Paper plane today. This has been a fantastic episode and discussion. And I have one question, and then Mark, you can ask the Kevin Kelly question.
Great.
And you can totally say, I don't want to answer this question.
Okay.
But we mentioned some books that we've read. Irreducible is one of them. Federico Fajan, who basically created the Intel 4004 first microprocessor, like he turned down the path of neuroscience. He turned down the path of, dare we say, quasi-spirituality.
Yeah.
Quantum information panpsychism.
Quantum information panpsychism. If you haven't read the book, I think you would love it.
I wrote it down when you guys said it, Irreducible. I'm actually fascinated by it.
So in Irreducible, Federico Fajan believes that the quantum wave collapse actually proves that free will exists. What do you think about that?
Ooh, that's deep. Let me, I will, as I'm thinking, I'll make a couple of high level comments. I think the overlap between spirituality, religion, philosophy, and quantum is absolutely fascinating. That Venn diagram overlap is really interesting to me. And if you look at the role religion has played in humanity over the last 5,000 years, it always seems like it is sort of explaining the sliver of the world that science hasn't yet addressed, right? So thunderclaps, thousands of years ago, those were the gods, right? That was Thor. And as we start to understand what those were, that didn't become associated with the gods anymore. And now you are at the point where one of the last things that we don't understand as humanity is quantum. It doesn't intuitively make sense to anyone. And so I do think there is a really interesting sliver of religiosity there. I'm religious. I'm a Catholic, and so I'm fascinated by this. But I do think there's something at the very core of what he's saying that makes sense to me, because I think there is something. If there is free will or not, or some higher power designed the world, they did it with quantum mechanics. They designed the universe, and so. Does the wave function collapse equal free will? I'd have to think about why that would be the case. But it's a really interesting thought. And at the broader perspective, I actually, totally buy into what he's saying. I think it's a fascinating topic to explore.
He says that the consciousness is a fundamental aspect of the universe and controlled by quantum units. We would love, because me and Jeremy, we are quantum curious, but we're by no means experts, and we'd love to speak to an expert about that book, just to really give us the scientific, because we'll believe anything we read to a certain extent. Yeah, it's a fun lesson.
Well, thanks for entertaining that. But yeah, read the book and circle back with us. Let us know if you want to have another chat about it.
I would, but actually, I welcome that. We should bring some of like the higher caliber quantum folks here at an Infleqtion in, because they can actually, Dana, our founder, would be the person you want to talk to about like what that means and why that might equate to free will.
Let's set it up. You've spoken about Dana. He sounds like an incredible person, so yes. The closer, the thinking on paper closer, the question that we end every show with, left by Kevin Kelly, wired founder, maverick, futurist.
Most interesting man in the world.
That's what they say. That's what Tim Ferriss says.
That's what Tim Ferriss says. Yeah, exactly.
What do we want humans to be, and how, if it does technology help us get there?
So our vision at Infleqtion is to harness the power of quantum to expand human potential. And if just, taken at the surface without explaining it, it sounds cheesy. But really at its core is harnessing quantum, which, as we've talked about, is the basic fundamental building block of nature, and applying that to allow humans to do things they weren't able to do before. And so maybe it's sort of a tangential answer, but what I want is for humans to be able to do things we haven't been able to do before, to continue to push society forward and solve some of our hardest problems. And I think quantum is an enabler to do that. And so I guess, what do I want humans to be? Maybe the answer is more, and quantum helps get us there.
Brilliant.
Very cool. What a great chat, Matt. Thanks so much for joining us. We're definitely gonna be tracking Infleqtion and definitely share updates as they come up. And like you said, maybe we have some more of your team on to chat. Mark, closing thoughts?
Well, watch this space, because I think we might do. Closing thoughts. It's been amazing. Every quantum conversation that we have at Thinking on Paper adds another layer to our understanding. And I think slowly, we're piecing it together, and it's starting to make more sense. So thank you for helping us with that. Thank you for our listeners, and be disruptive, stay curious.
Keep thinking on paper.
Wow. That was an emotional episode of Thinking on Paper. If you're still with us, and of course you are after that, if you have any questions about that show, email us at hello@thinkingonpaper.xyz, subscribe on the platform you're listening, and please, as a curious mind, share this with just one person in your life who would like to hear these conversations.
Maybe two. Share it with two.
Maybe two. Share it with two.